So good afternoon everyone, this is Arun Sharma from MIDAS and today we'll be covering bridge load rating, and we'll be talking about a two-span post-tension box girder bridge. So this is how we'll be going about the webinar today. We'll start by creating the bridge geometry from scratch. We'll define the materials and sections, then nodes and elements. On this we'll apply the boundary conditions and load the structure with static loads. After this we'll apply the pre-tension tendons to the structure for post-tensioning it, and we'll also perform the estimation of time-dependent losses for tendons as per AASHTO LRFT. We'll then go ahead and apply live loads as per AASHTO LRFT, for which we'll define two lanes on the structure, and then we'll apply two standard vehicles of HN93 onto the structure, and right after that we'll go ahead and apply the load rating data, for which we'll apply the longitudinal and shear reinforcement. The load rating parameters and rating cases will be defined, and then rating design will be performed. After this we'll share with you the results of the analysis. So this is the bridge elevation and the cross section that we are sharing. You can see there are two spans, 184 feet and 128.5 feet. There are two unequal spans. We have a fixed bearing at one end and the expansion bearing on the other two. You can also see the tendon layouts. We have inclined tendons in the exterior webs and straight tendons in the interior ones. So you can see this is a 3-cell box girder. The material properties and everything is shared here. So what we'll be doing here is, I'm sorry for the technical difficulties there. Yeah. So we'll apply the tendon properties as shown here, and then we'll apply the reinforcement data. I'll come to these slides a little later and we'll cover them in more detail once I am at that point. So for now what I'll do is go into the program itself and start modeling. So this is how MIDAS Civil window looks like. On the left hand side we have the works tab, where you can see everything that we'll be performing or applying to this model will be clearly listed down. So to start with, what I'll do is right click anywhere in the model view window, go to properties and select material, and in material I'll click add, and type of design I'll click concrete, and under material standard it will be ASTM reinforced concrete, and under the database we'll select C4500 PSI grade concrete. Then I'll click apply, and now go ahead and define a steel material for tendons. So I'll select type of design as steel, standard being ASTM steel. From DB I'll select A416270 low relaxation strand, and then click OK. Having done this, I can move on to the section tab and click add to define the section that I want to use. Since it's a pre-stressed concrete section or post-tension box girder, I'll go to PSC section tab And as you can see here, we have the various options of considering 1 cell, 2 cell, 3 cell, n cell 2. So here you can select any number of cells and create any kind of section you want. If you don't find the variations that are here sufficient and you are using something peculiar, then what you can do is click on PSC value tab and then either enter the section properties directly here, or you can define them by coordinate and create your section from scratch. You can also import your section from section property calculator, which is another tool built into the program itself, which allows you to bring in your section drawings from CAD DXF inputs. So you can bring your DXF drawing, calculate the section property, and then import it from SPC into the program and then use it. So there are various other variations possible in order to define the section. But let's say there's a particular type of section that you want to use and you have already defined in some other model file. So what you can do here is click on import and go to a model file from where you want to use the section, and the program will show you under the selected list the girder section that I want to use, and then I can click OK. And then if I click or double click on the section, you can see its dimensions and the layout. So having defined the materials and section, and you can also notice under the works tree the material and girder sections have been defined. So now I'll move on to defining the bridge layout. Since it's a very simple straightforward bridge, I'll go to model, structure wizard, and select a beam wizard where I can specify the distance. The units are in inches. So my first span was 184 feet, so I'll enter 184 times 12, comma, I'll have other span was 128.5 feet, so it will be 128.5 times 12. Then I'll click add. You can see the layout generated. Along with this, now I'll define the material and section, and then I'll click apply, and you can see the bridge created right there. I can close this and then proceed with the other modeling. There are several other ways of creating such simple geometries. This is just one of them which I showed you. Other than this, you can have all the curvilinear geometries that you can similarly generate in no time. Having done this, you can apply the boundary conditions. So for this, what I'll do is select the node, right click, go to boundaries, select support, and as I mentioned, my first abutment will have a fixed support, but the bending moment will be released. So Ry is released. Dx, dy, dz stands for 3 displacement degrees of freedom. Rx, Ry, and Rz stands for 3 rotational degrees of freedom. All of them which are checked are restrained. The ones which are released are checked off. Then I can click apply, and you can see that the support is applied to the structure. Then I'll use single select tool and select the other two nodes, and this time I'll release dx because I want it to be a roller support and allow the movement or the expansion, and then click apply. Now having created this geometry, I can click close here, and the program performs analysis for every element at 5 different points: I, j, half, 1/4, and 3/4. So in order to get a more accurate analysis, what we'll do is divide the existing girders into number of smaller elements. For this, I'll click on select all, which will select everything that is activated onto the screen. Right click, go to elements, and select divide. I'll have equal divisions, and number of divisions along local x-axis of the elements is 10, and then I'll click apply, and the program will divide the girder. So each span is divided into 10 pieces. Having done this, now I'll go ahead and apply the loads onto the structure. So click on load, static load cases, and here I'll enter the name as self weight, the type of load being DC. Click add, change the name from self weight to superimpose dead loads. Again, the type being dead load component and attachments, which is DC. Click add, and then I'll enter pre-stress force and the type being pre-stress, and then click add. So we have defined 3 load cases right now, and now I'll go ahead and define the assign values to these load cases. So right click, go to load, and then click on self weight, and in the load case name you can select self weight and the direction Z, enter -1, and then click add. So in this way we can define self weight of the structure. Having done this, you can click close, then right click again, go to loads, and now I'll apply superimpose dead loads as element beam loads. For this, I'll click on select all to select the entire structure and select the load case as SDL, and it is a uniformly distributed load. Now, other than uniformly distributed load, you can consider concentrated forces, moments, and torsions, and trapezoidal loads, moments and torsions, and uniform pressure or trapezoidal pressure. So there are so many variations that you can consider. If it's a wide bridge and you want to consider the eccentric loads due to the at the barrier location, you can choose to do that. Otherwise, you can check it off. So the loads are applied at the nodal location where the bridge is created, and then you can consider the values of loading. So the values with me is in kips per foot, and the units here are in kips per inch. So what I'll do is just change the unit from inch to foot, and then enter the value as minus, because it's in the gravitational direction, 0.15 kips per foot, and then click apply. So you can see the loading being applied to the structure. Now we are done with the static loads, and now we'll move ahead to define tendon loads. For this, we need to define the tendon property. Defining tendons in MIDAS Civil is pretty simple procedure. There are just 3 steps that you should go through. First is tendon property, second is tendon profile, and the third being tendon pre-stress loads. So in this sequence, you should go ahead and define your tendons. So what I'll do is change the unit back to inch, click on tendon property, click add, and then enter the name as tendon, internal post tension, the material being A416. Now for total tendon area, what you can do is either click on this button with 3 dots, select the tendon strand diameters and the number of tendons, and then click OK. The program will calculate and enter the total tendon area. Or if you have this value directly with you, let's say 4.3 square inch, you can directly use it. The duct diameter being 5 inches, and the relaxation coefficient you can select either based on Megura or other parameters, other codes. So we prefer using CEBFIP here. So I'll select CEBFIP. Then I'll go ahead and enter the ultimate strength, which is 270 KSI. Then the yield strength being 230 KSI. Curvature friction factor being 0.2, wall friction factor being 0, and then anchorage slip, as it was 3/8 of the inch, it is 0.625 at the beginning of that means at one end, and on the other end it is also 0.625. In MIDAS Civil, you can consider bonded or unbonded tendons just by selecting the appropriate option. Today we are talking about bonded tendons, so I'll stick with the bonded type. bonded tendons here. Click OK and then click close. So we have defined the tendon property. Now next step being defining tendon profile. Now for defining tendon profile there exists more than one ways. One is directly defining based on your spreadsheet inputs. The other ways can be using your text inputs, and the third way being you can import the tendon profile from your DXF format. But the most commonly used is the spreadsheet input, and this is what I'll be discussing now. So click add and enter the tendon name as, let's say, tendon 1, the tendon property being tendon, and the number of and the assigned elements. Now you can select through which element the tendon is passing and select them, or you can just click on and in this case, since we have the tendon running from one end directly to the other abutment, so I'll click on select all and select all the members that are there. So you can see assigned elements are 1 to 20. Then you can select the input type, can be either 2D or 3D. So I'll have 3D input, curve type being spline. So basically when you are giving the controlling points for the tendon, the interpolation is done for the tendon profile based on either spline or round curve. Then there is an option called typical tendon. When there is a number of tendon passing or following the same profile, then what you can do is just define one profile and multiply its effect by that many number of tendons. So let's say 6 tendons I want to have, and then you can go ahead and enter the coordinates. So if you have the coordinates with you, or you can directly enter them one by one, or if you have them in the spreadsheet, you can just open your spreadsheet, select the coordinates, make sure the unit systems are consistent. If they are in inches, in the program also it should be inch, and then click here and then Control V to paste it. And then you would like to fix those points where the curvature is changing, the slopes basically, or the point of inflections. So you can fix those points so the program will not interpolate those points, and any point intermediate might be interpolated as per spline curve. Having done this, you can then go ahead and specify the profile insertion point. So you have defined this profile. Now where in the entire model are these points? So this is what you have to specify. So the profile insertion point is the ith end of element number. So you can directly take your cursor to the element with respect to which you have defined these coordinates and then click here. So based on the offset location or the centroid location, I would rather say offset location of the box section or the section that you are using, these points are defined. So for the this coordinate system, the ith end of element number 1 is the origin. And since we are applying the tendon in the inclined web, you can give a rotation to it, the rotation being 18.5 degrees, and then you can click OK here. And if I go to the side front view, you can see tendon 1 numbers n is equal to 6, and they are within the inclined web. I'll repeat this once more for defining the tendon in the second web. I'll enter the name as tendon 2, property being tendon. I'll click select all, 1 to 20, input type 3D curve, and typical tendon being 6. There is something called profile reference axis. So for straight curves you can use, or sorry, for the straight bridges you can use the global XYZ coordinate to define your coordinate tendon points, tendon profile points. But if the bridge is curved, or you want to define it based on your own coordinate system, you can opt for the curve type reference axis. But if you want to define the tendon profile based on the element's local axis, then you should choose the element type of reference axis. So the advantage of this method is uh, if the layout of the bridge is not very straight, but it's like deviating, or it's along different curves, then if you don't want to define or change your coordinates of the tendons manually, you can consider the reference axis as element in order to consider or draw the tendon profile. So I forgot to mention this in the previous tendon layout, but nevertheless we covered it now. Now I'll select the tendon profile for the second one, copy, click here and just paste it, and fix the point of change in curvature. The endpoints are automatically fixed, so you need not fix them, but as you can see, the point is changing the elevation, so it's on minus 1.66, then it goes further down to minus 36 and then starts climbing up. So this means there is a change in the curvature. So you can see this crest and trough feature. So this is the first trough, so you can fix this point. The point of insertion being ith end of element number 1, and no rotation is needed, and I'll click OK, so you can see the tendon right there. And in MIDAS Civil there exist several ways of copying or replicating the tendons, because that is very often used. So what we can do is you can just click on the tendon that you want to copy or move, and then click on copy and move. You can enter the distance through which you want to move, so it will be 0, 129, 0. So basically what I'm trying to do is copy the tendon number 2 to the web number 3 as tendon number 3. So and since the elements are the same, so current assigned elements only. You can choose to move the tendon or create a copy of it. So here I'm trying to create a copy of it, therefore the mode is copy. And sometimes when the individual girders through which you are copying are not of same length, and there is some iota of difference in the length of the members. So by selecting the feature called auto adjustment of tendon length, the program will automatically adjust the length of tendon. It will reduce and it will shrink or expand the tendon to match the length of the girder to which it is being copied. Another very good feature in the software and very useful. And the source of this number, that is 129, is from the origin or the center point of the section. This first web is is 64.5 inches away. So I've taken twice of this distance so that I can move it along the y-axis. So it will be 0, 129, 0. And then I'll click OK. The moment you do that, you can see a copy of the tendon is created. And let me just modify the name of this tendon. It will be tendon 3. And then click OK. Now in the same manner, I can copy tendon number 1 to the location for tendon number 4 in the fourth girder. But there is another way of doing the same thing. I can just click on copy and move. If I don't know the distance between the two, I can just click OK, and the program will create a copy of the tendon at that same location. Now what I can do is double click in the tendon 1 copy and change the name from tendon 1 copy to tendon 4. Everything else remaining same, just the y coordinate is not minus 187 but plus 187.12. Then I can click on the next cell and then copy that value, and just like we do in spreadsheets, paste it. So we have changed the y coordinate for the tendon, and the rotation will be, instead of 18.5, it will be minus 18.5, and then you just click OK. So you can see the tendons created. If you want to display them, you can just right click and display. So in this manner, in no time you can apply several tendons. If you want to apply using the text inputs, you can easily do that. You can go to tools, you can go to MCD command shell, you can enter TDN, tendon property, you can choose tendon profile, and then click insert command. So this is the command in which you have to enter. So if you have information in text, you can format it in this as per the syntax and then click run to create it. Or you can, if you want to create a text file out of these tendon profiles, once you have entered, you can click on insert data, and there you go. You will find the tendon name and all the coordinates and the information given here: tendon 2, tendon 3, and tendon 4. So it has a very well integrated with the notepads or text formats as well as in spreadsheet inputs. Now moving on to defining the tendon prestress loads, which is the third and the final step for defining tendon profile. So I'll click on defining prestress loads, then I'll select prestress, and then I'll select all the 4 tendons and put them under the selected list, and the jacking will be done simultaneously at both ends, and the stress value will be 189 kSI at both ends, and then click add. Now since we are not doing any construction stage analysis, the time dependent losses for the tendons need to be assessed based on the approximate method that is given in AASHTO LRFD. And for doing that, you can now click on analysis and then find approximate estimate of time dependent tendon losses, and it is as per AASHTO LRFD. You can enter the ambient relative humidity, let's say 70%, the mean compressive strength of the concrete at the time of initial loading, let's say 3.5 kSI, relaxation loss as per code, tendon type is low relaxation strand, and the tendon load is defined in the load case as pre-stress, and the self weight is defined in the load case as self weight. So you can add that and then click OK. So now once the analysis is done, the program will take into account the losses as per AASHTO LRFD, the formulas that are given there. Now we'll move ahead and define the live loads onto the structure. Let me go to the ISO view, and for doing that you can just find the moving tab right here, and then go ahead and define the moving load code, which is AASHTO LRFD, and then click OK. Once you do that, you can see several other options being activated. Now before moving ahead and defining anything like lanes and vehicles and load cases, let me first assign the structure into different structure groups. For this, what we'll do, we'll go to the group tab, go to structure group, right click, select new with 3 dots, and enter the name as bridge girder. So this is one structure group, and I'll click select all so that you can select the entire structure and then assign it to the bridge girder. But before doing that, let me define the other structure group as well. So other will be span, and let's say you want to create multiple groups but changing the suffix, so you can enter 1 to 2 and then click add, so you'll get span 1 and span 2 structure groups. So once you have defined the structure groups and you have selected the entire bridge girder, you can just click on the structure group, drag it over the screen and drop it, and you can see 21 nodes and 20 elements have been selected in this structure group. Now I'll use single select tool and probably go to the elevation and select span 1 as shown here and put them under span 1, and then I can select span 2 and put them under span 2. Now how I figured out where span 1 ends and span 2 starts is the difference in the segment division. As you can see, the spans whose number are 11 and 2. 11th is 1/10 of 184 feet, whereas 2 is 1/10 of 128.5 feet. So therefore the difference in the length goes to show where the two different spans starts. Now let me display the node numbers or the element numbers. And having defined the structure groups, now I can proceed to define the lanes. So you can click on define traffic lanes and then click add, enter the lane name as L1. Then you can define the eccentricity from the center line of the elements, which is minus 127.5 inches. Vehicular load distribution through lane elements, because we are not dealing with grillage or cross beams here. And the moving direction for the vehicle will be both forward and backward, so I have selected both. And the selection will be based on 2-point system, so I'll click on the first point and then go all the way towards the end and select the last point, and the program will create the lane for us. So I'll switch to the top view before I click OK, so that you can see the lane created. So if you are selecting the girders from left to right, then related to this direction of selection, towards the left side the eccentricity is negative, towards the right side it is positive, and that will become more clear once I define my second lane. So it will be lane 2 or L2. I'll enter the eccentricity as 76.5 inches. Again, distribution through lane element from 2 points starting from first to the last, and then click OK. So you can see the lane applied right here. Now you may even notice the lanes are not symmetric about the center line of the bridge, and it is on purpose. We are leaving some space if we happen to have sidewalk or barrier on one side, not on the other side. So making it more realistic, most of the time the bridge alignment and the lane alignment need not be symmetric. So the idea is you can have different layout of the lanes on the bridge, and as long as the lane layout is as per AASHTO LRFD, you are okay with any kind of lane layout. Now I'll define lane support negative moment at interior piers. Basically, as per AASHTO LRFD clause number 3, you need to maximize the negative moment over interior piers. So program needs to find out which are the spans or that fall on the either side of the interior support. That is first thing, so that it can apply the vehicles on either side of the interior support at the given spacing, and take out the lanes. Take out the axles that reduce the negative moment at that interior pier. So in order to consider these clauses of AASHTO LRFD, we'll select as per auto input and select the bridge girder group and click add. So basically the program will consider automatically where the negative moment zone is occurring on this girder group, and then will optimize the negative moment for you. Then I'll click close here, and then the next step is to specify lane support reaction at interior piers. So basically you need to specify where your interior support are located. So I unselect everything and then just directly go to the interior support node and click apply, and in this manner I'll select and apply the lane support reactions at interior piers. Having done this, I'll close it and move on to the green color icon which shows a vehicle, which is for define vehicle. I click on add standard, enter HL93 truck vehicle with a dynamic load allowance of 33%, and then click apply. I'll change the vehicular load name from HL93 truck to HL93 tandem, and the dynamic load allowance being 33, and then click OK. So in this manner we define two vehicles. Now I'll click on add user defined, and then I'll select permit vehicle and enter the vehicular load name as permit, and the impact factor being 0. And this is a very powerful tool that allows you to define any kind of vehicular loading onto the structure. It can be asymmetric, it can be symmetric, it can have uniform axles, it can have different type of axles. So as you can see here, axle 1, axle 2 and axle 3 all are different from each other. Axle 1 is a 2-wheel axle, axle 3 is a 4-wheel axle, and axle 3 is also a 4-wheel axle, but the arrangement of wheel about the central line of the bridge is different. So in this way you can go on creating any number of axles and then use them in any number of combination to create a really big vehicle. And this feature was brought in as per the contract with Ashto from Caltrans, and this was a customized development for Caltrans for the first time, and now it's available in the public domain for all our users to get take benefit from it. Now you can enter the axle. Let's say axle 1 is A1, and then I'll enter P1 being the load of the wheel. So as you can see from this second bitmap image, P1 is single wheel, D1 is its distance from the center line of the wheel, center line of the vehicle. So P1 being 50, D1 being, let's say, 12 inches, and it's just a 2-wheel axle, so it's a symmetric vehicle. So I'll just define 1/2 and click add. Then I'll change the name to A1 to A2, and let's define a 4-wheel axle where we have evenly distributed wheel load. So basically, if we have entered P1 as 50, the program will automatically keep P2, P3, P4, P5, any number of wheels we have on the one side of the central line of the vehicle will be replicated on the other side, and all their values will be same. So we'll have P2 also as 50, but we just need to enter the spacing from the center line, which is D2, which happens to be 24 inches, and then you can click add. So we have defined 2 lanes. Now we'll define the vehicle in the combination of these axles. So first axle is A1, second axle is A2, second axle is also A1, third axle is A2, and fourth axle is also A2. So we have defined a 4-axle vehicle with 2 2-wheel axles in the front, then 2 4-wheel axle in the rear. And the spacing between them will be, let's say, first and second axle are 60 inches apart. The second and third are also 60 inches apart. The third and fourth are 72 inches. And the fourth one being last is obviously the end. So in this manner, you can create any user-defined vehicle in no time with any kind of axle arrangement. You can choose to have variable spacing between them, so the program will automatically vary from a minimum value to a maximum value, the spacing of axles automatically. Then you can click OK here and click close to complete the vehicle definition. Now we'll move ahead and define the moving load cases. So I'll click add, enter the name as standard for standard vehicles. I'll click add, select the vehicle, minimum number of loaded lanes being 0, maximum being 2, and select L1 and L2 as the 2 lanes on which this particular vehicle will be applied. So the program will consider the cases where no vehicle is running only on one lane, vehicle is running on all lanes, so L1 and L2 together. Then you will click OK. Then again click add, change the vehicular load type from HL93 tandem to HL93 truck, and repeat the same. And then click OK. Now the program will consider these two as 2 independent scenarios, and then find which is the worst case combination, and then spit out the results in that manner for the worst case condition. Then you can click OK here. Now I'll create one more load case for permit vehicles, so I'll click add, and then you can enter the name, let's say permit, and you can check on load case for permit vehicles. So this is a different type of dialog box, and you can select the permit vehicle which we defined, which is permit. Then the reference lane. The point to be noted here is that lanes are defined with respect to the offset location of the bridge, but the location of permit vehicle center line is defined based on a reference lane which has already been defined, and here you can give the eccentricity from that reference lane as 2.5 inches and then click OK. So you've defined two moving load cases here, and then you can go to analysis and select moving load analysis control data, where you can select what kind of analysis method you want to use, where you want to how you want to apply the load points based on influence line dependent points or all points. Influence line dependent points is something which we expect and want to do as per ASHTO LRFT to take out the excels where uh, we don't need their effect to minimize the negative bending moment. So in this manner you can choose the two options, but in some cases where let's say it's a train loading and you cannot take out some axles in between, so you can choose to apply on all points as well. Then the influence generating points is at 3 locations per element you can generate influence lines, and I mean basically you can apply the load at 3 points along the segment, and then the program will generate the influence line based on this. You can increase or decrease the number, and this will uh, by and large control the analysis speed. More the number, more higher this number, longer will be the analysis. Lesser this number, lesser will be the analysis time. So 3 is something optimum we have decided, and we are kept as a default, but you can always alter it based on your needs. Then analysis results, we have an option called for frames called normal plus concurrent forces. Basically all other live load analysis produce envelope results only, whereas in MIDAS Civil, if you just check on this button, you will not only get the envelope results but also the concurrent forces associated with it. So for a given bending moment, what is the shear and corresponding axial force will be automatically generated by the program in separate text formats, separate spreadsheet formats. Then you can click OK here, and now we are ready to define the bridge load rating data. So we'll start by defining the reinforcement. For this I'll go to model structure wizard and then select PSC bridge, where you can give the span information. Basically you don't want each and every segment to be considered as a span while doing this design, so you can specify a group of element to be a part of one span. So what I'll do is I'll give the girder name as, let's say, G1, and I'll select I'll assign the elements as per selection. So I'll click on select all, so entire bridge is selected, and then I'll click add replace, and then I'll go ahead and say add. Now once you have done that, you can see the ith end is the ith end of the first member, and the jth end is not there because it will be the ith end of the member number 2, and then for the finally we have the 20th element which is at the jth end of the span. So we have defined the span information. Now I can click close here and then go ahead and go to model structure wizard and select under PSC bridge section and reinforcement. Since our box girder is uniform, it's not tapering or varying depth, so I'll not modify the section data along the longitudinal length of the bridge, but I'll do define the reinforcement data. So for reinforcement, you can select which girder you want to use. You can enter the division tolerance that you want to have, and then you can select various start points. Now this is the point I'll go into the program, into the slide, and show you how to enter the rebar data. This is a very common way of representing the rebar data and very frequently used on the West Coast. I've seen several drawing from our West Coast client which have similar way of representing the data. So the program is designed to cater all these kinds of needs for you. So what we have in here is you can identify the bend cap location as support number, and then on the one side it is going 45 inches, the other side is going 37 inches, and one is the left side and the right side, and this is the edge of the deck. So you can see the spacing also from the edge of the girder to the center line of that rebar, and thereby you can go ahead and define the layout. So I'll do exactly in the same order. So all you need to remember is it's 45 feet on one side, 35 on the other side from the bend cap location. So let me just escape this here. Now you can select support 1, support 2 and support 3. So I'll go to support 2, which happens to be the bend cap locations. The distance, if I give negative, this means it will go on the towards span 1. So I'll enter minus 45 feet times 12, that means inches, and the end point for that, the reference point, is same as the start point. So now from the same start point I'll give the ending point, which will be 37 feet in the other direction, and therefore I'm adding it as positive. Now you can select what diameter of rebar you want to use. Let's say 8 feet, sorry, 8 number of rebar being 11, with reference point being centroid, y being 11, top 2 inches, and the spacing being 44 inches, and then you can click add to define the rebar layout. Then for the second time we have 37 on one side, and this will have a negative sign, sorry, my bad, minus 37 times 12, and this time on the other side it will be 45 times 12. Everything remains same except the centroid from plus 11 will go to minus 11, and then you can click add. So in this manner you can go ahead and define all the longitudinal rebar layout in your bridge. Then you can go to shear reinforcement and select what kind of shear reinforcement you want to have. It's a diagonal reinforcement, and the pitch being 12 inches, and the angle being 90 degrees, and area being 3.5 square inch. And you can specify this from support 1, starting from one of the end going up to 96 inches. You can click add, and this so and so forth. You can go ahead and define all the rebar data. You can once you have done this hard work, you can always save this as a wizard file and open it up in any other model file with simpler dimensions, and then tweak things here and there a bit. So if I click on open one of the wizard file, and then you can see the data can be easily brought in no time. But since this is incomplete data that I have shown here, but for the timing I'll just click OK to show you with the example. So the program will automatically divide the members where as per our criteria where the rebars are ending and starting. So the program will automatically divide. So we started with just one type of section. Now we are with several other sections, and I can go into the reinforcement and double click on any one of the sections, and let me pick any section as random, and then you can see here the longitudinal reinforcement. If I just click on this line, so you can see the reinforcement data shown right there. You can click escape here. So the rebar data, as you can see, is given here for longitudinal layout. For shear reinforcement also you can see the rebar data is entered here. So in this manner you can verify all the sections where the rebar is starting and ending. So you can see here the arrow heading showing the rebar locations and how many layers of rebar exist at that location. In this manner you can quickly verify your data. So what I'll do is go ahead and open the model file where I've accurately done this rebar definition, as you can see here. And now I'll go ahead and enter the rating data. So I'll go to design, I'll go to bridge load rating design, I'll click on rating design code, I'll select the rating design code here as H2LRFR, I'll click OK, go back to design, bridge load rating design, I'll define the rating case here. So you have two limit states. I'll go first for the strength limit. I'll enter the maximum DC factor as 1.2, minimum as let's say 1, and then select the load case to which I want to consider this. So I'll select both the DC type, that is self-weight and superimposed dead loads, and then I'll come to the secondary effects, and I'll have the multiplying factor as 0.9 and selecting pre-stress load case, which is primarily for the secondary effects of the tendon. And then you can select from the primary, you can give the light load combination as primary vehicle being permanent vehicle with a factor of 1.75, let's say, and the adjacent vehicle being standard vehicle, and you can enter the name of this rating case as RC strength. Click add here, and then I can go to service limit, and here I'll stick to 1 in the as shown here, and for secondary also the factor is 1, but for primary vehicle the factor is changed from 1.75 to 1.25. I'll change the name from RC strength to RC service, and then click add. So in this way you can define your rating cases. Then close this, go back to design, bridge load rating design, go to rating parameters where you can define the system factor, how you want to consider the flexure, how you want to consider the shear. If it's a non-segmental or segmental bridge, you can give the service limit state strength for compressive strength. Compressive strength is stresses for compressive stress is the limit is 3.5 ksi. For tensile it is 1. You can even give 0 if you want. Then pre-stressing steel is, let's say, tensile stress is 30 ksi, and then you can click OK. So once you have defined these factors, then you can go to design and then go to rating group design. So here you can specify different span with different condition factors. So which the span that has deteriorated more, you can give them an appropriate condition factor, and the ones which is relatively better condition, you can give them a different condition factor. So if you want to have based on the deterioration of the structure, you can choose different condition factors for different spans. So that is the basic idea for this option. So right now we have used just a factor of 1 for both, and then I'll go back to design, and then I'll specify the material that we are using. So we are using a 4500 grade PSI concrete, which will have rebar as grade 460 and sub rebar also as 60. If you want, you can choose from different other grades that are available, and then you can click modify and then close. And then you can go ahead and click on rating design to perform the design of the structure. But in order to save some time, what I'll do is I'll just stop this execution for now and go to open the completed model file which I have here. And now focus on some results. So I'll go into the bridge load rating design tables. First of all, I'll see the rating results summary for service. I'll check on the service rating case that I defined, and the program shows here that my the minimum rating factor is 1.9 at this location, and the relative location is given as 0.4 L1 G1. That means along the girder 1.4 of span 1, we are getting the minimum rating factor is 1.96, and the allowable stresses and the demand and everything is being laid out in neat fashion. And if you have temperature gradient, the program will take care of all the factors and then go through all the permutation combination in order to generate the results. So you can see then it says that the tensile concrete tensile stress is not satisfying, and you can see some kind of noise here. So you can pinpoint the location where this is occurring, 11th member number 11th at jth end, and which is happens to be the 1 times L1, which is the complete length of the span 1. So I would say at the interior support where negative moment is occurring, so maybe the tensile stresses are exceeding. So you can see and verify what are the causes for this, and you can see the primary vehicle effect at that location is quite low, and therefore it is giving such kind of value. So you can pinpoint the location where you are getting what kind of results and then verify and correct them, and tendons are showing a good result here. Then I'll go into design, tables, and then similarly we'll see the summary of reinforced concrete, the rating case for strength. And here you can see the minimum factor is 1.385, and this is the capacity, this is the demand. Let me change this value from KSI to kips and foot, so that you can see the foot kips as capacity here, demand, and the factors. So this is okay here. And then you can see the detailed reports if you want by going into bridge load rating design, tables, and then if you click on concrete stress, then it will show you for tension and compression. So basically under tension the section is failing, so you can modify and see the reasons for that, whereas compression it is giving okay results. Then you can choose to see the tendon precessing results at I and J end. So the best part is when defining the rating case, the program clearly gives you which cases is being compared. So DC max, DW max, T plus, TG plus. So basically DC is the type of load case, and the max means the value that you enter in the two columns for maximum and minimum. So the program takes into account the combinations from there. So all the combinations are shown here, and under all combinations we are getting okay results. Then you can further explore other results. Let's say flexure rating data. You can see for flexure rating data these sections are okay here. And let me close the other tabs here and then go to design and see it in a diagram representation. So you can select all rating cases, which includes both your strength and service. I want to see what is the rating factors along the length of the girder for flexure. I can enter the scale factor and then click apply. So you can see at this point there is very high values. So what I'll do is, since it's flexure and at the supports I'm not really interested, so what I can do is select some number of girders within the mid span and then click activated. So you can see the values along the girder in the mid span for flexure, which happens to be about 1.5 to 1.4 1.5 to 0.14 in this region. So you can so it's not, this value is not occurring in this zone. This is the overall value that you are seeing, but anyways, this is the result for any particular location that you want to see the load rating factors. So all these tables that you saw, all the diagrams that you see here, and the and other results are fully Excel compatible. You can directly right click and export them into your spreadsheets, and in fact you can create a report within the program itself in no time. But because of time crunches, I'll not dwell much into it, and instead of instead of discussing it today, maybe in some other webinar we'll be talking more about the report generating features. So that's all I wish to cover with you today. If you have any questions or comments, you can leave the comments at the following email address. So we are getting some questions here. What is number of tendon meaning? So basically, the certain tendons are clubbed together and represented as one tendon. So you can define just one tendon profile, and in fact, as you can see in this display, also there's just one tendon profile, and we entered number of tendons is 6. So what the program will do, it will have one tendon property, one profile, and its effect will be multiplied by 6, so that it represents as if there were 6 tendons in the close vicinity of the profile, and this profile is representing the centroid location of that tendon group. So does that answer your question? Great. Now we have more questions coming in.